welcome back. We're in the home stretch here. We've finished chapter 16 on electricity. I'm going to spend a little bit of time over our last three notes, this one included, looking at magnetism and its relationship to electricity. So as we work through this last little bit here, I might go through a little bit faster than I would normally do, but I just want you to get a bit of a sense for the topics that we're going to be covering as we work through this. So again, just be looking to the calendar here, seeing that we're going to be doing 17.1 and 2 today, 17.3 and 4 tomorrow, and then I'm going to talk just kind of roughly on the 22nd about chapter 18 and electromagnetic induction, which is how we use magnetism to create electricity, right, for our society. Right, so in other words, how does a generator work? So the next 2 days are going to be looking at perhaps how an electric motor works, or building up to how an electric motor works. At the end of chapter 17, I've got a video link to a YouTube video that you can go and have a look at a way of building a simple electric motor if you are interested. And other than that, chapter 18 will be the reverse. It's using magnetism to make electricity versus using electricity to make magnetism. Right, so for today I'm going to start with chapter 17.1 and 2. Again, just reminding you that I am still planning for our final test here on the 24th. I don't think I'm going to do that live class here on the Monday, but I will know better by tonight if I'm going to need that live class. I do want to have a live class either for chapter 18 or as review before our test. The live class that I did on Tuesday, I was the only one there, so I'm not sure whether that's necessarily worth planning. If you're not needing it, then perhaps it's just a little bit of a waste of my time to go ahead and do that. So, all right, so let's get into chapter 17. So chapter 17, we're going to start by looking at magnetism in general, and then we'll move into electromagnetism. So the first part of chapter 17 looks at magnetic fields. Now, we've already learned a little bit about fields when we talked about gravity, because when we talk about gravity, we know that if I jump in the air or if I drop something off the roof, there's a force, an invisible force that's pulling objects down. And we know that the magnitude of that force can be demonstrated, but it can also be quantified. It can be calculated as to the amount of gravitational field. I often like to think of a magnetic field as something comparable to a gravitational field in that it has a lot of very similar properties. So if I look at how do we calculate gravitational force, well, we discovered this, or we went through this earlier in chapter 5 when we said the gravitational force is proportional to the magnitude of the masses that are attracting each other, inversely proportional to the separation distance squared, and that there's a constant that makes this all work so that my force turns out to be in newtons. All right, so that's what big G is there for, is it to take those numbers in the units of kilograms, and meters, and finally come up with an answer in newtons. Right? We come up with big G, the universal gravitation constant. Now, what I know about the gravitational field is that it is always an attractive force. Right? There's no anti-gravity. Right? At least not the way not the way we understand gravity. So gravity is always a force of attraction, and it's we can use that force to generate energy, gravitational energy, and we can do the same thing with electricity. So in grade 12, when you take 4U physics, we will spend a bunch of time talking firstly about gravitational fields again, but then we're going to transfer that same knowledge, that's the same principles, to our understanding of electric fields. Now, an electric field is very similar. An object that has charge, right, has a field surrounding it. And if it gets near another object with charge, the field of one will interfere with or impact on the field of the other, and as they kind of work together, they will create either an attractive force or a repulsive force, force of repulsion, based upon a very similar formula. The formula says if I want to measure the amount of electrostatic force between two objects with charges Q1 and Q2, where Q is the amount of charge on the object, electric charge, if they have more charge, I will get more force of attraction or repulsion, right? And if they get closer together, I will increase my force of attraction or repulsion also. Instead of using my universal gravitation constant here, big G, I'm going to use something called Coulomb's constant. Coulomb did well here in the naming of things, and as such, we've got another constant that allows us to look at the relationship between the quantities of electric charge and the force of attraction or repulsion. Okay, enter magnetism. So it turns out magnetism is similar also. Right? It's more similar to electric fields even than gravitational fields, but it turns out that ultimately it has to do with the properties of matter again. The first one was about their mass, the second one here is about their electric charge, and this one is about their magnetic properties. So we're going to be talking about magnetic strength with P for pole strength. I'm talking about poles of magnets, right? The amount of force of attraction or repulsion is going to be equal to some constant, and again, this is a variable, times P1 times P2, where P1 and P2 are the magnitudes of the pole strengths, how strong is the force of repulsion or attraction, and divided by the separation distance squared. So this field idea applies itself to all of these different situations, but they're just based upon different properties of matter. Now, if I look down towards my laws of magnetism are very similar to my law of electrostatics that says opposite poles will attract and like poles will repel. And the closer they get together, the stronger becomes that force. Again, as R gets smaller, the bigger becomes F. Right? As P's get bigger, the bigger becomes F, but as R gets smaller, because in the denominator, the stronger becomes the force. So these two magnets here may be sitting on the desk in front of me, and they're pulling, but they're not strong enough to overcome the friction between the desk and the magnet, so they're wanting to come together, but they're not strong enough. If I push them a bit closer together, at some point, click, they will actually attract and pull each other together because the force will get strong enough to overcome the friction which is holding them on the desk in front of me. Now, if I look at that magnetic field, one of the things about magnetic fields like gravity and electrostatic fields is it's always there, right? You can't turn that field on and off. It's a property of the matter itself. Now, the very first described magnet was described in an area of Greece called Magnesia, which is why it's called, it was found in a stone. The stone was found to be attracted to other stones. You think, well, rocks shouldn't attract rocks. Well, some of these rocks contained a mineral called magnetite, right? And magnetite in Magnesia gave rise to the idea of magnets. Now, what they found was if they took a sample of this magnetite and basically suspended it on a string, it would always orient itself, so it would always point in the same direction. And we know today that's how a compass works. A compass needle is a magnet, and it aligns itself with the magnetic field of the planet. So Earth has a huge magnetic field, and if I put a magnet, again, what we used to do in the grade 10 course many years ago is when it contained a unit on magnetism, is you could actually take a small piece of cork and you could soak it in a tub and then take a small needle that's been magnetized, set it in there, and it would always point towards the North Pole of the planet. Right? And if I turned it so it was sideways, it would reorient itself over time so it pointed towards the North Pole of the planet. Right? Because there's a field that doesn't just go up and down like gravity, it travels around the planet and it has direction. Now, because of that, people have been using compasses for hundreds of years, maybe thousands of years, for navigation purposes to get from point A to point B, across the ocean, through a desert, through a forest, right? When you need to be able to find direction, but it's hard to find landmarks to orient your direction, then we use a compass to do that, which is, again, just a magnet. So when I look at the planet itself has a magnetic field. Let's just go down to the planet here. And the magnetic field is based upon a core that goes from the North Pole down to the South Pole. It runs right through the planet, right? And it turns out that what I have at the top of the planet is a south pole of the Earth's magnetic field. So when I take a compass here and I'm sitting here in Hamilton and I've got a compass, it's pointing towards what we call the North Pole. But again, if the north of my compass is actually a magnet itself, remember, opposites attract. So it turns out that the North Pole of my compass is attracted to what we would have called the North Pole on Earth, but it's actually a magnetic South Pole. Yeah, hopefully you're not confused yet. Okay, so that's the planet Earth, right? And what we know about the planet Earth now is that we have identified the North and South Poles on the planet, and the North Pole on Earth then isn't really a magnetic north, it's actually a north-seeking spot, which is a South Pole. Okay, so it attracts the north of the magnets that are compasses on Earth, and the north of the compasses points in the direction of where we first put that flag and called this the Earth's North Pole when we first got there. And that North Pole basically is still there today. However, what we're seeing is if we go back with our compass up to where the north that flag is, we'll find, oh, North Pole isn't at the flag anymore. North Pole's way over there. It turns out that the magnetic field of the planet is shifting. Right, it's continually shifting, and as time goes by, it rotates. It moves in a pattern around the North Pole, what we would have called the actual North Pole. Well, it's shifting, right? And again, it's scientists are predicting that we may have a reversal of the Earth's magnetic field again. What that means for us, I'm not totally sure, because a lot of our devices are based upon GPS systems, are based upon well, maybe not GPS systems. It'll be based upon some type of technologies that are based upon navigation using traditional electromagnetic fields. So, just like a gravitational field, I know the magnetic field is invisible, right? We typically draw fields using what we call field lines, right? And the field lines always have three basic rules, right? Field lines always point away from north towards south. So you're going to see that when we come to chapter 17. Away from north and towards south. Field lines will never cross each other, and the closer I put the lines together, the stronger is the strength of that field. Okay, so let's move down here. So if I take a compass here, so here's my compass, and I put the compass here on the right side of the magnet, the North Pole, the black side, will be attracted to the South Pole of that bar magnet. As I move the magnet around, the compass needle is going to shift until I'm rotated 180 degrees, so black is now facing where the black was facing the magnet before. Now the black is moving away from the magnet because the South Pole of the compass needle is attracted to the North Pole of that bar magnet. And for all these spots, the black is always pointed either towards south, or the white is pointed away from, black is pointed towards south and the whites are pointed either towards north or away from south. Okay, so there's our direction for these magnetic fields. So we've got this field around the planet, and again, if this was the Earth and I could turn it sideways 180 degrees so that the north is at the north, actually put the south at the top and the north of the bar magnet at the bottom, we'd see that the black needles always point towards the North Pole. Okay, so there's a little bit of history Okay, so what makes a magnetic material magnetic? Well, we have something called domain theory. Domain theory, when I looked at those very first minerals, the magnetite minerals, they were magnetic because they were formed geologically with the planet containing three important elements, mostly nickel, cobalt, and iron. Now, today we have discovered we can make magnets using other elements that will have magnetic properties. Probably the most important one is neodymium. It makes very, very powerful magnets. Again, it's an element on the periodic table. And if I use neodymium, it's actually spelled wrong there, I can create very, very strong magnets. So what is it about the element that makes the material magnetic? Well, it turns out that within the material itself are little clusters of these atoms, of these different three elements, nickel, cobalt, and iron, and the clusters of atoms are called domains, right? So this is domain theory. So a cluster of atoms is called a domain, and the domains have direction, which can be north and south, or dipole, right? Two possible poles. Each domain has two possible poles, and if the domains are all misaligned, like I have in this nickel here, right? This nickel is not magnetic because all of the domains that are in here, the dipoles are all pointing in different directions, and they cancel each other out. If I was to take this same nickel and take all of the domains and align them so they were all pointing in the same direction, what I would do is create turn the nickel into a magnet that has a north pole and a south pole at the opposite end. Now we can do that using a magnet. If I actually take a strong magnet, and put it right here with the north pole of the magnet right beside the bar magnet near the nickel, what it will do is it will attract all of the south poles of the dipoles that are here within the nickel would all get pulled towards the north pole here, which means the north poles of all these arrows now point this way. And what that does is it makes the other end of the nickel magnetic, such that it has properties of a north pole. Hopefully that makes sense. So that's part of our understanding of how domain theory works, is that these clusters of atoms, called domains, have the possibility of having magnetic properties, and when they align, I end up with inducing that field. So what they showed here in this little diagram is if I take the north pole of a magnet and put it beside a nail, all of the dipoles inside this steel nail will align themselves so that the south pole of the dipoles is pulled towards north on this magnet, and the north poles all point south. Now if I take another nail and bring it close, what it will do is the north pole of this second magnet here, the north pole of this nail will actually cause all the dipoles in the second nail to align. They'll all get pulled, so the south end of them gets pulled towards the north end of the nail, making this side of the nail south, this side of the nail north, and now the north of this nail is attracted to the south of this nail, and they will attract to each other. And then the same thing will happen. The north on this nail will align all of the domains here, the dipoles that are in this third nail, such that the souths are all attracted to this north up here, right? And then they'll align. And you can see that if the original inducing magnet is strong enough, I can get many of these things to line up because I just keep inducing. But as I get further and further, the effect gets diluted because it's not a perfect transfer of magnetic field throughout the entire chain of nails. So, fun, interesting. Maybe you've been to a birthday party when you were 5 and somebody gave you a magnet in your goodie bag, and you've played with it a little bit, right? So they can be fun. However, there's a lot of applications for magnetic fields, right? Probably the most important one in our lives would be that of electric motors and generators. So an electric motor is basically anything that uses electricity to cause a rotating effect, to cause a turning motion. Right? That's what an electric motor does. It causes something to turn. Generators do the opposite. They take something that's turning and use it to make electricity. So these two are the opposite of each other. Electric motors are the second half of Chapter 17, and generators are Chapter 18 of the last couple of notes here. Now today we're using magnetic fields to do other things, such as magnetic levitation trains. Magnetic levitation, again, what causes a train to basically wear out, parts that wear out, causing a lot of energy required to move, is the amount of friction that happens inside that train. Give it its strength, to give it the ability to carry the amount of weight that it does. They get heavy and there's a lot of contact and things break down and wear down, and it's not a great system. So we use magnetic levitation. So if I create the same pole in the track and in the train will actually hover above the ground, and it will basically be floating in air. If you look on YouTube, maybe before my next video, I'll see if I can find a couple of videos that I've seen of magnetic levitation experiments. Some of them involving one at McMaster, where they've got a magnetic levitation train on a toy one that basically hovers above the track, and if you give it a push, it goes around and around and around hovering above the track because of the magnetic field. We use magnetic fields in particle accelerators, such as the one in CERN in Switzerland. A lot of this is how we have started to understand what the universe is made up of, the different types of particles. And again, a lot of our understanding of matter has come from particle accelerators, and we accelerate particles by using magnetism to generate the force, right? Magnetic force, and that causes the particles to move. Some of you may have had an MRI. MRIs are magnetic resonance imaging, and again, it's using magnetic fields to look at the inside of objects without actually having to open them up, such as ourselves, maybe our brains, our organs, our bodies, right? We can actually look at what's going on by using magnetic fields and magnetic resonance imaging, or MRI. We also have some natural things that happen, such as northern lights, the aurora borealis. And again, what's happening is the magnetic fields of the planet attract particles that are coming from the sun that have charge, and as they get close, movement of charges, as we're going to see soon, generates its own magnetic field, which will interfere or interact with the magnetic field of the Earth. And as it interacts with our magnetic field, it will move relative to the planet instead of traveling in a straight line from the sun, which is what it would have been doing before we came along and interfered with it. And then sometimes when we're trying to figure out how do those monarch butterflies get from that beach in Mexico to this same part of Hamilton every year? I mean, that's thousands of miles that they've got to fly, and they always end up either on that same beach or back in the same place here in Ontario. So we've come to understand that a lot of migration patterns involve the natural use of natural magnetic properties inside living organisms to help them guide their migrations. Okay, so there's magnetism, and like I said, it's kind of fun, but ultimately, I want to be able to use magnetism. Okay, understanding how a magnetic levitation train works is terrifically cool and interesting, but again, how are we making this happen? So let's go back to Christian Ørsted was a physicist who was looking at electricity and looking at magnetism, and he said, I'm sure. He said, when I look at these two things, there's a lot in common between these two things. Right? First off, there's two opposite possibilities. For electricity, it's positive and negative. For magnetism, it's north and south. We have two types of forces that can exist. If they're both formed in the same form, we'll have repulsion, and if they're in the opposite orientation, we'll have attraction. In other words, positives and negatives, will attract, positives, positives, negatives, negatives will repel. Norths and souths will attract, north, north, and south, south will repel. They're looking very similar. They both cause invisible fields that will surround the objects that are generating them, right? And they have direction and they have shape, right? Again, very important, seeing that the two are very, very similar. And then lastly, and maybe not quite as related, but he said if I rub two objects together, I can generate some of this stuff. And ultimately, we know that for static electric charge from chapter 15, but the same thing happens with a magnet. If I take a magnet, and I take a nail, and I take the magnet and I pull it down the nail a bunch of times in the same direction, what it will do is it will align the domains that are within that nail, and I can turn that nail into a magnet, right? By taking this magnet and pulling it along the length of that nail a bunch of times, right? Ultimately, what I'm going to do is I'm going to pull all the south domains to here and leave the north domains not wanting to be near that north that's been close to the magnet, and as such I will generate a magnet out of that nail. So just like we saw with static charge, if I rub things together I can create static. Oersted said if I rub a magnet through near a non-magnetic material, I can generate this type of effect also. So he was convinced something's going on here. Either magnetism and electricity are the same thing, and we're just not figuring this out yet, or maybe magnetism and electricity are just two different forms of something that are related, like water and ice, or maybe I just don't know yet. So he spent a lot of time trying to figure it out, and ultimately he said, I'm going to try something. So he took a magnet, he took a compass, which we know is a magnet, right? The compass needle is a magnet, and he aligned it with the wire and pointed them towards the North Pole. Right? So here we are. Here's the compass pointing towards the North Pole, and here's a wire underneath the compass with no electricity turned on. Okay? And then he turned the electricity on so it was running through the wire, and automatically, clip, it went straight to the side. It pointed 90 degrees perpendicular to the direction that it was originally pointing. And he turned it off, and it went back to pointing north, and he turned the electricity on, and again, bip, straight away. It didn't just slowly cruise over there. It automatically went directly to east. Right? Now, if he turned the direction of the current around in the opposite direction, right, so that he put instead of having positive at one end and negative on the other, if he flipped them around, right, so I had negative on the one end and positive on the other, the needle pointed the opposite direction, showing that there is a magnetic field around the wire, right? When the wire has electricity moving through it, there is a magnetic field. If there's no electricity moving through the wire, it has no magnetic field. And then when I change the direction of the electric current, I reverse the direction of the magnetic field. Reverse the direction for the current, reverse the direction for the magnetic field. So I'm now starting to see that there's a relationship here. He also took the wire that was perpendicular where the compass current is on, and the compass is pointing towards the south. If you took the same compass and just kind of slid it under the wire, it now points to the north. He said, I wonder why above it's south, and what if I turn it around so the wire is perpendicular, and I'm going to move the compass to different locations around that wire. Okay, if we have a look at what we see here, I can see that once the current gets turned on, so with the current turned off, as I have here, all of these compasses are pointing towards what would be the North Pole in wherever this room was set up. So the reds are all pointing towards the North Pole. As soon as I turn the current on, these things all now move so that they have a direction around the wire, right? If I change the direction of the electricity, the reds all reverse themselves, so they're going in the opposite direction. So what this tells me is a number of things. Okay, and again, this is probably one of the more important parts of this whole section. Right? If I have a current carrying conductor, right? In other words, there's electricity moving through a wire. I'm going to have a magnetic field around that wire that is circular around the wire. Okay, number two, the field gets stronger as I get closer to the wire. And number three, that circular field has direction. We say because we understand the way a clock works as clockwise, and we understand the way a clock works in reverse would be counterclockwise. So our two directions become, instead of being north, south, up, down, left, right, it's clockwise or counterclockwise. So what I can see in the B picture here is the field is going around this way, right, where the red's going towards the back. It goes behind the wire and then around to the front. So it's kind of going counterclockwise. Right? It's going in the opposite direction. Clock would go this way, right? This is going the opposite direction, right? So it has a direction, and our direction is defined in terms of clockwise or counterclockwise. So on the right here, I've got a piece of wire going through a cardboard, and we're going to move electricity through that wire and then scatter a bunch of small iron dust on the cardboard. And what happens is the iron dust will line itself up with the field rings, right, around the wire, showing the circular pattern of that magnetic field, right? And as much as that field would be invisible around the wire without the paper and the pieces of iron, we can see that we now can visually see or detect that circular magnetic field around the wire. So, Ernst, I wonder, I need to have a way to decide which direction the field is going to go. Because again, think about using magnets for navigation. You don't want to be out in the middle of a lake where you can't see shore anywhere, and you think, I wonder which way I need to go. Get your compass out, and it points one direction. You think, oh, so there's north. But if for some reason it changed 180 degrees and was pointing in the other direction, you'd be going due south. So I need to know which way this magnetic field is working. So we came up with what we call the right-hand rule for straight conductors. Now, let's talk about the right-hand rule for a minute, and then I'm going to maybe muddy the waters a little bit. So the right-hand rule says if I look at a conductor like a wire, and I use my right hand and wrap the hand around the wire so that my thumb is pointing in the direction of the conventional current. Okay, this is the important piece here. Okay, conventional current, not electron flow, but positive flow. Remember, positives don't flow. We talked about this before. Right, so as the negatives move, it pushes a positive space up in the opposite direction to the electron flow. So conventional flow is really like the movement of positives, even though they don't move. And we have to use our right hand. Okay, this is critical here. And it shows me that my fingers are curling around the wire in the direction of that magnetic field. In this case, it's going to be counterclockwise for the person in the picture there. Okay, so the fingers curl in the direction of that magnetic field. So like I said, in this example here, I'm seeing that it's counterclockwise. Okay, our two possibilities are clockwise or counterclockwise. In this case, it's counterclockwise. Okay, the opposite to the direction that the clock should be traveling. Okay, so that's called the right-hand rule for conductors. So, when I'm looking at a wire, okay, sometimes I'm not looking at a wire that's going up-down, like this one here. The wire could be maybe going left-right, like the one that's here, Or maybe the wire is going away from me like I have here. These two wires here are wires that I'm basically looking at. If you can imagine holding the pencil up in front of yourself so that you're looking at the eraser and that the pencil is pointed directly away from your face, right? That's the direction for the wire here. So you're looking at this wire. Now, one of two things could be happening. Either electrons could be coming towards you through that wire, or they could be going away from you through that wire. So what we've done is, again, the convention says if I see a dot in the middle of the wire, that tells me the electrons are coming towards me. If I see an X in the middle of that wire, it's as if the electrons are moving down that pencil, down that conductor, away from me. So dots mean towards me, X's mean away from me. Now, so again, if I'm looking at the page and the wire is coming out of the page, the one on the right here is showing electrons coming out of the page towards me. This one shows them going in. Think, well, how do you remember which is which? We always think of an arrow. Okay, so think about what an arrow looks like. Okay, so the arrow has got a head, it's got a shaft on the end. If that arrow is coming towards you, what you're going to see is the point of the arrow coming towards you. If the arrow is going away from you, you're going to see the four parts of the quill here, because there should be four parts to this quill. There should be four parts to that quill, and you'll be seeing the back end of the quill moving away from you. So if you see the dot, the point's coming towards you, electrons are coming towards you, or I guess positives are coming towards you. And if you see the quill, the positives are moving away from you. You're seeing the back end of the arrow, the back end of the motion. So if I look at the pictures on the bottom here, A and B, I'm going to use my right hand and I'm going to wrap it around that wire. Okay, so slide them under the wire and then curl them over with my right thumb pointing towards the direction for conventional current, which is to the right. Okay. So if that's happening, I can see my fingers are going around the bottom and wrapping up over top. They're coming from the bottom and they are going that direction. Coming from the bottom and disappearing back under the bottom. So there's my direction for the magnetic field here. Right? They're coming underneath, again, my right hand, going under the wire with my thumb pointing to the right, and that's showing me that the direction for the field is up and over top of the wire. If I look at the B example there, I can see the direction for the field. So that's the direction my fingers need to move. So my fingers now are going to move over top of the wire, right hand, over top of the wire, and notice which way my thumb is pointing? My thumb is pointing to the left. So what that's telling me is that the conventional flow is in the B wire is to the left. Here, electrons are moving right. Here, electrons are moving left. Here, my thumb is pointing right, and my fingers are under the wire coming up. Here, my thumb is pointing right because my fingers are wrapping around the wire from the top and pointing to the left. Okay, so these take a little bit of getting used to. When we come back to doing our live class on Monday, I will take some of this up. So I might just record the live class when it's convenient, and I'll just leave you the video posted for you to get to. Okay, so there's a bunch of examples down here, right, and I'm going to leave you with those 1 to 7 to work on. Okay, but I'm not quite done yet. Now, if you could imagine, the second part of this chapter 17.2 talks about things called solenoids. A solenoid is a coil. So if you can imagine going to the store and buying a spool of string, right? And the string is wrapped, so it usually comes wrapped on a piece of cardboard. Whoops. Usually comes wrapped on a piece of cardboard, and the string, usually when you get to the end, they go back on itself. You get to this end, and it goes back on itself, right? And you've got several hundred meters of the string wrapped around itself. If I replace the string with a conductor like copper wire, this isn't just a spool of string now, it becomes what we call a coil or a solenoid. So again, if you could imagine taking your finger, put a fingernail on here, and wrapping a piece of wire around your finger a bunch of times, that would become a solenoid or a coil. Now, in Ampere's experiment, he's trying to figure out if I create a magnetic field around a coil. So what happens in a coil is I generate a magnetic field Okay, so let me take a step backwards here. Okay, so a coil is just looped wire. So let's just look at what happens here. If I take a loop of wire, I'm going to switch out of here onto my whiteboard for a minute. So here's my wire, and this is the direction for conventional flow. So my hand goes so that I'm lying it flat on my iPad right now with my thumb pointing to the right, and I'm seeing that I actually have to go under. I can't go over top. My fingers won't go backwards. My hand doesn't do that. Right? My fingers go under the wire and they curl around, so the direction for the magnetic field goes this way. Okay, the direction is over the top and then down towards the bottom, and then it will disappear around the back of the wire. Now, what if I take a piece of wire and create a bit of a loop? Okay, and I'm going to do the same thing. Conventional flow is that way. So what's happening here again? If you could imagine electrons, again, the direction for conventional flow is that way, and with my thumb pointing towards the right, I can see that the field does this. Okay, and over here it's doing the same thing. But what about when I get to the loop here? So if you could imagine, if I turn my iPad 90 degrees so that I'm over here now, as the electrons are coming through here, right, they are still moving to the right, towards the top of my iPad, right, and my fingers wrap around it and show that the direction is coming through the middle of that loop. And if I turn my iPad another 90 degrees, because again, remember the electrons are going this way, right? If I show the direction for electron flow at the top, I can see that the electric field, magnetic field, is coming from the center of the loop out. And if I go to the next side and show the direction for electron flow on this side over here, I can see that it again is coming from the center of the loop out. So it really looks, if I was to hold the loop straight up and look straight down it, so I'm looking down, I'm not even sure how to draw this. This is a lot easier to do on a blackboard. If you could imagine, there's actually a magnetic field that basically is coming out. Remember, the dot means out. Of that field towards me, it's going into the bottom of that loop and out of the top of that loop. So again, if I was looking at that loop, I've got the wire on this side and wire on that side, I'd have the magnetic field going that way out of the loop and going this way into the loop, and it actually has direction. Now if I take a second loop of wire and do that, I end up with twice as much magnetic field coming through the center. And if I add another one, I make the field stronger. And as I keep looping my wire around and around and around and around, I make the field that's coming through the loop. It has one direction. It's now polar, right? It's got a north pole and a south pole. It's going to ultimately generate a field based upon the direction for the conventional flow and based upon the direction that the electrons the flow is moving through that coil. So let's go back to the note here. And we're going to come up with a second rule here, which is called the right-hand rule for solenoids or for coils. Whoops. What have I done? So here's my coil of wire here. Looped around, looped around, looped around. And as the electrons are coming out of the field towards me here and going in at the top, and then coming out towards me at the bottom and going in at the top. If you can imagine, again, using your right hand to show, if at the bottom here, if I put my hand down at the bottom here, whoops, with my thumb pointing towards me out of one of those dots, and I wrap my right fingers, I can see which direction they point. They point this way. For all three of these dots, if my thumb is pointing towards me out of my iPad and I wrap my fingers around, I can see that it curves so that I'm generating a field there. And if I look at the ones on top, if I take my thumb and point it for this one here, point it away from me, because that's what the X means, right? X means I'm seeing the shaft. I'm seeing the back end going away from me. My fingers will curl around the other way, right? They're coming around this way, and they will push that way. And the second one does the same thing, and the third one does the same thing, and the fourth one does the same thing. And ultimately what I end up doing is I create the equivalent of a bar magnet, right? This, with the electrons moving through it, is the same as this. The nice thing is I can turn this one on and off. I can make this one stronger by making the electrons move, the electrons or the conventional current move faster. I can make this stronger by adding more coils, right? There's a lot of things I can do to make this like this, but to have options now, right? I can make it variable so that I can make it meet my needs, whatever my needs are. So, like I said, to make this electromagnet, so again, if I turn the electricity off, it's just a piece of wire now. It has not magnetic anymore. It doesn't do anything, right? It has no attraction for things that can be magnetized or attracted magnetically, ferromagnetic substances. So how do I make the electromagnet stronger? So like I said, three things, right? More turns or more loops on my coil, faster current flow, right? Or what we sometimes do is to increase the amount of magnetic flow, a field through here. I will take a material that is ferromagnetic. That means it can take a magnetic field and carry a magnetic field, and I'm going to push it up through the center of the coil here. And what that does is this piece of iron that I just pushed in there that's not magnetic, as soon as I turn the electricity on, boom, this becomes a hugely magnetic North Pole and South Pole, which I can turn off when I turn the electricity off or turn back on again. So by putting a ferromagnetic substance in there, I can make this coil even stronger. Now the question becomes, like Ørsted thought originally, how do I decide which end of this is going to be the North Pole and which end is going to be the South Pole? Well, we came up with a second right-hand rule. This right-hand rule for coils or solenoids. And basically it says if you use your right hand and you wrap your right hand around the coil, such that your fingers are pointing in the direction for conventional flow, your thumb will point towards the North Pole of your electromagnet. So if you can see this coil right here, if I push the electrons up from, or the conventional flow from this side, goes up and around the back, comes back forward and disappears around the back, and the coil comes up the front and disappears around the back. It's always coming yeah, it's always doing the same thing, and at the very end it comes up the front and then disappears down the back. Okay, so my fingers show that the current is coming up the front and rolling over towards the back, and my right thumb shows the direction for north. Right? My right thumb shows the direction for north. So as the electrons, conventional flow, moves up and then disappears around the back, my fingers have to do the same. Come up the front and disappear around the back, and my thumb points to north. Now, we use electromagnets for a lot of different things, and it's critical that we know which end is north and which end is south, because I'm either going to get attraction or repulsion. If I'm trying to attract something, I don't want it to repel. I want to know what the effect is going to be when I turn my electromagnet on. All right, so we use electromagnets for a lot of different things. Our textbook shows you some pictures of electromagnets used for traditional speakers. Right? Again, if you watch a speaker, speakers have got very strong magnets in them, and basically they will cause the cones to move back and forth, giving us different frequencies and different intensities, and ultimately I can make the different sounds that I was trying to generate using my speaker. If I have an electric bell, electric bells are the same. I'm pulling a little hammer onto the metal bell part, and it's ding-a-ling-ling-ling. Basically, every time it hits the bell, right, a magnet is pulling it onto the bell, so it strikes the bell. The starter in a car, if I've got power locks for my car, or power windows even, right, all these things use solenoids to make them work. So, like I said, really what I've done is I've given myself the ability to use magnetism how and when I want. I'm able to control when the magnet is there and when it's not there, and I'm allowed to even change the polarity. I should even say not just the intensity of the magnetism, but also the polarity of the magnetism. So if I took this coil up here and reversed the conventional flow, so now it's going this way, right? My right hand shows it coming around the back, rolling over the forward, and my thumb would now show, oh, north is now on the other side. So I can not only change how strong the magnet is by changing current and number of coils, I can also change which side of this is going to be north and which side is going to be south using the right hand rule for solenoids or coils. All right, so so if I look at the picture here for figure 7, it should say, I think it says conventional current. Let me double check in the textbook here. I think it should say conventional current. Yeah, it should say conventional current. Conventional current. So if I look at number 1, just for instance, and look at the one on the left-hand side, okay, again, my fingers are going to wrap around this wire. So here's the wire right here. I'm looking down the end of the wire. I can see that the field is going this way. So my fingers are going to wrap, my right hand is going to wrap around the field. And notice that means my thumb is pointing up towards my face, right? The answer here is going to be a dot to show that the direction for the conventional flow is towards me. If I look at the one on the right hand side here, on this side, again, if my fingers are coming up, my right hand are coming up around the left side of that wire, my thumb is pointing, oh, now it's pointing down through that wire. So the one on the left here becomes an X in the center of that dot to show that the conventional current is moving away from me. If I look at C there, I can see that the positives, conventional flow, are on the bottom. So again, I'm just going to turn my iPad. I find it easier to turn my iPad. So my fingers are now above that electromagnet, showing that the conventional flow is coming up the front and disappearing around the back. And what that means is the North Pole is here, the South Pole is here. All right, so remember, positive is where the conventional flow is coming from, negative is where it's being attracted to. For D, this is positive, the big side is positive, the little side is negative. All right, so I'm going to leave you with those to try. I'm going to erase those because I want you to do them again on your own. Okay, but again, remember, like I said, which side is positive and which side is negative. All right, so I'm going to stop there for today. Tomorrow I'm going to come back and I'm going to look at what's called the motor principle. I'll probably make this video tonight before I go to bed. But I'll leave you with those 7 questions there. And then there were questions before on just the right-hand rule for conductors. Now, before I close, you're going to see in the textbook that they have 2 sets of rules. They have right-hand rules and left-hand rules. You think, okay, so how are we going to figure out which one to use? And what is the difference between a right-hand rule and a left-hand rule? Right-hand rules work when we're talking about the direction for conventional or positive flow. Remember, if the positive flow here is moving this direction, that means negatives are moving the opposite direction. Right? If positives are going one way, negatives must be going the other way. If I'm talking about electron flow, I have to use my left hand. If I'm talking about conventional positive flow, I use my right hand. Now, the question is, so they both work. They both give you the same answer, and the question becomes, why? How do we decide which one to use? Right? Why are we choosing right-hand rules instead of left-hand rules? If you look in your textbook, depending on which version of our textbook you have, some of them give you all of the questions and answers using the left-hand rules, and some of them you give all the questions and answers using the right-hand rules. They will all give you the same answer. It just depends what's moving. Are electrons moving, or are positive spaces moving? Right? Do we have conventional flow? So, historically, when we thought what's moving, before we understood what a proton, a neutron, and an electron were, we knew something moved through wires. Right? Electricity moves through wires. We knew that. What is electricity? We got no idea. But something is moving through our wires here. And then we ultimately, Benjamin Franklin and his kite experiment and a lot of other things, but gave us some kind of idea that it was actually electric charge is what electricity is. It's positives and negatives. And the question was, so what's moving? Well, it must be positives moving, right? Why would negatives move? It's got to be positives moving. So our original understanding of electricity was based upon the notion that it's positive charge moving through conductors that ultimately create electricity. Today we know that it's not the case. It's electrons moving. Think, well, why wouldn't we change all the books? Well, that would mean changing a lot of books. If the right-hand rules work, then we don't need to go and change all the rules. We just need to tell people that we're talking about conventional flow and not electron flow. So in your textbook on page 585, it says, depending which book you've got, in the main body of the book it says left-hand rule for conductors, or it might say right-hand rule for conductors. The one I'm looking at right now says left-hand rule for conductors. If you're looking at the one that's online that I posted, it actually says right-hand rule for conductors. They've changed the word left for right. And then in the bottom right corner of that same page, it says, oh, and by the way, we're talking left-hand rule here, but there's also a right-hand rule. And it says the right-hand rule is used for conventional flow, where the left-hand rule is used for electron flow. And if you move to 586, 587, it talks about the left-hand rule for conductors, for coils. But on the side of the page, it says there's also a right-hand rule. So again, we're going to say right is right. We're going to use our right hand, right, to show what happens in terms of our motion, because the questions are going to talk specifically about current, which is conventional current, the movement of positive charge. Okay, so that's probably the most confusing thing. That's probably the most confusing thing in this whole chapter, is the idea of right-hand rules versus left-hand rules. So I'd say, remember, right is right. Stick with the right-hand rules, and we're talking about the movement of conventional flow or positive charge through our circuits, and hopefully you'll be able to keep it all straight. So I'm going to stop there for now. I will come back to this. That's a long one. The next two are all pretty long too. Notice that there's no math involved here, just a lot of theory. I do want you to be able to understand